Today we're going to look at free body diagrams. It's something that is used a lot in physics. The reason we use free body diagrams is to isolate the external or internal forces, I guess internal forces, that are acting upon an object. So there you have it. They're visual representations of force and object interactions. So it's the interaction between whatever number of forces and the object that the forces are acting upon. There are different conventions for the ways that you can draw free body diagrams. I like to draw them based on where exactly on the object the forces are interacting. So if I have a situation where there's a person pushing on a box and they're trying to move that box, this is how I would draw the free body diagram for the box. I first would draw the box isolated, so you don't show any of the surroundings, you just show the forces that are acting upon the box. Usually you have the force of the weight of the box, but then we also have the force of a person pushing the box, so force of the push, force push, and then also maybe there's friction here, so it's the force of the friction. So the ground is pushing back. If it's not moving, then the force here. Well, you could either draw it like that. Some people draw it like that. It doesn't. It's not super important. I don't know. I prefer to draw like that. It's just some force that's opposing it. If the force that's used to push the box is bigger than the force of friction, then you draw the force arrow. For friction, you draw that smaller, shorter. If the person is pushing and the box isn't moving, maybe the forces are equal in length, so then the box wouldn't move, or the forces are unbalanced, so it doesn't matter. There's so much friction that you're not even overcoming anything. So actually the friction would just be equal if it's not moving. But we'll get into that later. So that's how I would draw free body diagrams. You isolate the object and you just draw the forces upon the object with arrows. So let's take a look at our first example. Suppose you have a stack of books, each weighing 5 pounds. Draw a free body diagram, FBD, free body diagram, for the top book. And we're going to say that's the history book. So how do we do this? The first thing that we're going to do is isolate the object that we're drawing the free body diagram for. So I'm going to take the history book and I'm going to isolate it. I'm going to draw it all by itself. So that's the first thing. Maybe I'll get rid of this arrow so you don't think it's a force. The next step is to draw the applied and normal forces. Now, what the heck does that mean? And maybe I'll write this down, but when an object is in contact with a second object, the second object, if it's a supporting object, so if you're in contact with the ground, or you're sitting on a chair, or a book is resting on another book, and it's being supported by a second object, the second object can be replaced by what's called normal force. And then the applied force is just any force that's being applied against the normal force. So it's the weight of the book, or if somebody's pushing down, then it would be the weight of the book and the force of somebody pushing down on the book. Or an applied force would be the force that's pushing down on the book, or the weight of the book that's pushing down against the support. And then if somebody's trying to slide the book across a desk, then that's also an applied force. So a supporting force is pretty much a normal force. So here we go. Now, since this book was just sitting, maybe I should have drawn there. It's just resting on top of the math book. The force that the math book is pushing back on the history book is the normal force. It's the supporting force. So you could, some people draw the normal force like this. Some people draw the normal force going up this way. It's fine. I would say this would be Fn because it's supporting the book, and since the book is not moving, the applied force, the 5 pounds, that'll be the weight of the book. It'll have the same length arrow. So the applied force, that'll be 5 pounds, 5 pounds of force. And let me write that better. Since the book is not moving, the normal force is equal to the applied force. If they were unequal, then the book would move up or down. So that's for every action there's an equal and opposite reaction. That's one of Newton's laws. And there you go. That's the free body diagram on the top of book. All right, let's take a look at this example, and maybe we'll go on to a different part video. We got a giant, or maybe like an adult, pulling a sled with 2 very anorexic babies, very skinny babies. They're all skinny. Oh, they're just stick figures. I get it. So create a free body diagram for the sled in the picture below. All right. So the first thing you're supposed to do, if you're trying to create a free body diagram, is to isolate the item that you're trying to draw the free body diagram for. So we're going to isolate the sled. So we're not going to draw anything on the sled except for just the sled. And then, like, you could even just draw it as a box. Some people would just draw the sled as a box. And in fact, I'm going to do that because it's easier. So what are the forces that are acting upon this box sled thing? Well, I definitely have some angle here. That angle, I don't know what it is. I'm going to call it theta, the Greek letter theta. That angle, I don't know what that angle is, but this is definitely a force. The adult is pulling on the sled, hopefully to make the sled go so the kids can stop whining. But there's the applied force that the adult is pulling, so I'm going to say this is an applied force. So Fa, it's an applied force. And it's applied at some angle theta. We don't know that angle, but it's applied at some angle theta. So we have that. That's for sure something maybe it's easy to see. What other forces are acting upon this? Well, we do have 2 kids just sitting on top of the sled. So those are also applied forces, right? It's the weight of the children. So there's the weight of kid 1, weight of kid 2, and also the weight of the sled. We'll say that the sled is lighter than these fat kids. These fat, skinny kids. That doesn't make sense. Maybe it's the same. Close to the same. So we have, force of child 1, or the weight. The weight is the force. So we have all of those things. And we got the normal force. The normal forces on the I mean, it's just the opposite of those. And I would put the normal force going upwards, because hopefully it's not moving up or down. That would be weird. You'd sink down into the earth or just float up in the air. That doesn't make sense. And then also there's a force due to friction. So, like, I mean, the friction force is all across the bottom, but I would just put something like this, the force due to friction. And we can kind of pay attention to the, if the friction is small because it's on snow, then you make the force vector small. So this is the force due to friction. And there you go. This is a free body diagram. There you go. Isn't that beautiful? No, this guy doesn't like it. All right, we're going to move on to a different video.